Hello everyone, hello world, welcome to my corner of the internet. My name is Jeff and today I'm going to be talking about a lot of exciting and interesting content to come. Extremely long story short, I am part of the camp that believes a new golden age of computing is about to come. And the reason why is because the machine learning approach to artificial intelligence, the success of it is challenging a lot of the original assumptions that were held in the design of our compilers and chips 50 years ago. And so as a low-level systems programmer, I am interested in bringing this golden age to fruition. And I am going to be working on two projects, a software 1.0 language, which is C-like, and a software 2.0 language, which is going to be pytorch-like. And I'm going to be implementing both languages line by line from scratch and presenting it here. Right, so each language, the C-like language and the pytorch-like language, are going to have two phases each. For the C-like language, the first phase is implementing an interpreter for C0. C0 is a safe version of C, which is formally specified by some folks at CMU. And then we're going to modify that interpreter to turn it into a compiler, and it's going to compile C89 and target RISC-V, and we're going to target the RV32I instruction set. So that's a nice pathway because the front end of the interpreter compiler won't change much, because the way the original person that designed C0, we'll get into him later, designed C0 was for the syntax to be almost a perfect subset of C. And so of course the semantics are going to change because it's C, but it's going to be a nice transition. And then similarly for the PyTorch-like language for the software 2.0 stack, we are going to be first implementing a compiler that compiles an array-based programming language that provides tensor constructs with auto differentiation, and then compiling it down to NVIDIA Metal, something PTX-like, and being able to run neural networks on NVIDIA GPUs. Right, and then the second phase of the software 2.0 project is that we're going to be adding a new target architecture to the back end, and we are going to be targeting a TPU, but a TPU that you can buy, not a TPU in the cloud like Google's. And so this is a TTorrent dev kit. It's the E150, and so this is fundamentally a TPU because there's just many tensor cores in this chip. So that's that. And speaking about TTorrent, this brings me to the next part I want to talk about, which is Jim Keller, who's currently running TTorrent and started it, has a great chart here that captures the essence of the different objects that we're computing throughout the past, 50 years, 60 years, 2020. So before we were computing scalars, now we're computing vectors, and soon enough we're going to be able to compute tensors quite efficiently. I mean, not soon enough, sorry. We already are. And this is fundamentally why I am going through the two projects, because I think having a strong foundation in just regular compiler language infrastructure is going to have a lot of transfer for when you're building infrastructure for the software 2.0 stack. Even though the workloads that you're supporting are going to be computing tensors rather than scalars, there's a lot that transfers. And so to finish off this part of the introductory video, I am going to be building both languages in Rust, line by line from scratch. And the reason why I'm doing this is because Rust is a new systems programming language that essentially solves the tension between speed and safety. And so traditionally, if you want a fast language, you would have to use C and C++, which are unsafe. And then if you want it to be more safe, you would have to use something with a garbage collector. So you would have safety, but obviously you're paying the price of the garbage collector. So Rust solves that by actually, not really solves in terms of the tension, but actually there's like a third axis of that of this tension, which is just type complexity. And so it introduces a type system with ownership, which solves this tension. Not really, it's just choosing a third part of this tripartite axis. And so I'm going to be implementing all of this in Rust. And so there's no hard prerequisites for the content that's about to come. If you're in college, you just need to know how to program. So finish your CS1, CS2. And if you're a working programmer in industry, you're already a programmer. The caveat though is that I'm not going to be teaching any Rust. So if you want to follow along in Rust, feel free to learn it as we go and catch up on what you need. And it's also okay to follow along and implement the languages in a different language and a different host language. And that might actually improve your transfer of understanding even more than if you were following it in Rust. This is my website, and here, let me zoom in a little bit because I know everything is probably too small. These are the two projects that I worked on. And so the past couple of months, I've been doing some more research, and these are the two projects that I'm going to be implementing with you all line by line from scratch in Rust. So we got the first one, Pico C089, the second one, Pico Grad, the C-like language, and then the pytorch-like language. All right, that is it. That is all. Thank you all for watching. And if you are interested in low-level systems programming, particularly compilers, we will still understand what's on top and beneath us in terms of like the math of AI and the chips and stuff like that. But we're not going to be, providing lean code for math or Verilog for chips. We're going to be implementing a compiler for two languages. And if you're interested in that, you're interested in Rust, you're interested in this new wave of computing that's going to bring in what I believe and what many others believe is this new golden age, a lot more resources on my website. If you're interested in that, stick around because some very exciting things are about to come. All right, peace.